Okay, here we have notes for 5.1. We're talking about rules of exponents here, and there are a few of these. We're going to start with the product rule for exponents. So what this is about is how, and you can see some example problems here, what happens when you multiply things that are raised to powers by other things, and we'll look at division and exponentiation too. But I'm going to go through sort of what's really going on with some examples just with numbers. So say I have 5 cubed times 5 to the 4th. And after I go through these examples with numbers, we'll go into the more general rule. But if you can think about it like this will really help you as you go forward into the variable situations, because it can help you remember which rule is which, because this can be a little bit confusing. So 5 to the 3rd power, what that is 5 times 5 times 5. And now that is being multiplied by 5 to the 4th power. So 5 times 5 times 5 times 5. And so what we're asking here when I multiply these things is, how many total factors of 5 are there here? I have 3 factors of 5 from the 5 cubed, and then from the 5 to the 4th, I have 4 factors of 5. So then the total number of factors of 5 I have, all of these guys, I have 3 plus 4 equals 7. And so what I end up with for my final answer here is 5 to the 3rd times 5 to the 4th equals 5 to the 7th. And then I have this general rule for multiplying things to powers. So product, I'm talking about multiplication. A to the power of m times a to the power of n. So this is the same base, like the 5 is the same, but then they're being raised to different powers. The product of those two things, they're being multiplied, is a to the power of m plus n. And so here I've got a bunch of examples. The first one's just with numbers. I have 2 squared, so 2 to the 2nd power. So I end up with times 2 to the 3rd power, so I have 2 to the power of 2 plus 3, and that gives me 2 to the 5th. Now sometimes when it's a number like this, 2 to the 5th isn't so crazy, so I can pretty easily simplify that to 2, 4, 8, 16, 32. So my final answer here could be 32. But now here where I have just variables, I'm not able to do that. So here x to the 7th times x to the 9th. I have 7 factors of x here. I have 9 factors of x here. So the total number of factors of x I have are 7 plus 9. And that gives me x to the power of 16. Here, remember, if I have something that's just written by itself, like this y, that's considered to be to the 1st power. So here I have y to the power of 1 plus 5. So that's y to the 6th. And then this same thing holds if I have a whole bunch of factors. So like over here I have y. I have 3 factors of y from the first one. I have 2 more from the second factor here, and then from the 3rd factor I have 5, so I end up with a total of y to the 10th. So that rule isn't so hard, but you have been conditioned your whole life correctly to, when you see multiplication, multiply numbers. So this is something, and I talk about this all the time, strong mathematicians will say 2 to the 6th. Because they see multiplication, their brain sees a 2 and a 3 and a multiplication symbol and wants to multiply. But just try to bring yourself back to this idea of what's happening, that what we're really talking about is counting these repeated factors, counting how many times 5 is being multiplied by itself, or how many times y is being multiplied by itself. Okay, so now we have this rule for exponents, and I'll do another number example here. So let's just start with say I have 2 to the third power, and I'm raising that now to the fourth power. So what that means is to raise something to the fourth power means to multiply it by itself that many times. So to the fourth power means multiply by itself 4 times. So what I end up with is 2 cubed times 2 cubed times 2 cubed times 2 cubed. And then, again, what I'm doing is I'm counting up factors. I want to see what that final exponent is going to be. So this is 2 times 2 times 2 times 2 times 2 times 2 times, and this is kind of a lot of writing. So this is a good motivation to have a nice rule we can use instead of having to write 1,000 factors of 2 every time. But I think this really does illustrate what's going on. So here I have 2 cubed times 2 cubed times 2 cubed times 2 cubed. Now I'm counting up my factors of 2. There's 3 here, 3 here, 3 here, and 3 here. So the total number of factors of 2 I have is 2 to the 3, 6, 9, 12. And so what's happening, I have 4 groups of size 3. That is our basic definition of multiplication. So my general rule here says that if I have a, so some base, a to the power of m, and then that whole thing is raised to the power of n, my result is a to the power of m times n. So when I'm exponentiating powers, I multiply those exponents. So here, 2 cubed to the 5th, instead of writing out all those 2's, this is just going to be 2 to the power of 3 times 5, and that gives you 2 to the 15. And so this, it's not that hard to do, but make sure you go through all those book problems and get some experience with this, because if you're anything like me, you'll be surprised by the number of mistakes you might make. And this is something it's really tempting to just add these numbers or do 6 to the power of 4, but you're multiplying because this is x to the 6th times x to the 6th times x to the 6th times x to the 6th. So I end up with x to the power of 24. I'm counting factors of x. Now here I have -3 to the 7th times to the power of 7 times 5. And now you can get a little confused here. This -3 to the 7th, that's the thing that's getting raised to the 5th. So these parentheses around the -3 are just there to make sure you know that that negative goes with the 3. And so my answer here at the end is -3 to the power of 7 times 5, which is 35. Okay, on to the next page. Okay, so here on page 2, we have the power of a product rule for exponents. So what's happening here is I have 2 different bases. So let's say I have x times y, and then that product is being raised to some power. So let's just say 3 for now. So now what's happening here is that means that x times y, xy, cubed is xy times xy times xy. And now, because multiplication is commutative, I can multiply in any order I want. So I'll write that because multiplication is commutative, I can rewrite this in any order. So why not put all the x's together and have x times x times x times y times y times y. And so what I end up with is x cubed times y cubed. So this looks a little similar to the distributive property, but what's happening here is I have multiplication inside these parentheses. If I have multiplication only, then that power goes to both of those things. And the reason that that happens is because of this repeated multiplication. So this rule in general says this: if I have A times B, so two things being multiplied, and those things are being multiplied inside of parentheses, and they're being raised to the nth power, that then is equal to the first thing to the power of n times the second thing to the power of n. So here's a couple of examples. Here I have 5x cubed. That's 5 times x. Those things are being multiplied. So my result is going to be the first thing, 5 to the power of 3 times x to the power of 3. And now 5 cubed I can just kind of do. And so I can rewrite that as 125x cubed as a nice final answer. Now over here, this is an example of things getting a little more crazy. So I want to look at what two things are being multiplied here. And I'm actually going to rewrite this. So in my parentheses, some stuff is getting raised to the fifth power. The first thing that's getting raised to the fifth power is -2. And then the next thing is y to the fourth. So what happens when I do this is I have that -2 to the fifth power times y to the fourth to the fifth power. And this is where these problems start to get kind of interesting once we're using all these rules at once. So now over here I can just do -2 to the fifth. That's -32 because it's an odd power. And then y to the fourth to the fifth. To do that I need my exponent rule. So this is y to the fourth times y to the fourth, blah, blah, blah. I end up with a total of 20 factors of y, because when I take this power and raise it to a power, I multiply those powers. So I have y to the 20th, and then that is my final answer. Okay, just a couple more rules here. Power of a quotient. So remember, all multiplication is, or all division is multiplication by a reciprocal. So in general, rules that hold for multiplication will also hold for division. So here I have x divided by y to the power of, let's say, 4. What this is just x over y. So I have x over y times x over y times x over y times x over y. And now what happens, the way that multiplication of fractions works is I just multiply straight across the top. So I end up with x to the fourth. I multiply straight across the bottom, and I end up with y to the fourth. So what this rule says in general is if I have some fraction a over b, and that is being raised to a power, say n, that's going to be a to the n over b to the n. So let's look at a couple examples. This one's pretty straightforward. This is just the rule in practice. This is m over n to the seventh. That means I'm going to have m to the seventh over n to the seventh. So nothing too crazy in that one. And then I have here, there's a lot more going on. So what's happening is I have my numerator, I have x cubed, and that's getting raised to the fourth. And then in my denominator, I have 3y to the 5th. And that's getting raised to the 4th. So now, in my numerator, I have x cubed to the 4th. When I'm taking something to a power and bringing it to another power, I multiply those powers. So in my numerator, I have x to the 12th. In my denominator, things are a little more complicated. I have two things that are being multiplied that are getting raised to the 4th. So I have 3 to the 4th times y to the 5th to the 4th. And now I can get that all nice and simplified. My numerator already looks great. In my denominator, I have 3 to the 4th, which is the same as, let's see, 81. And then my y to the 5th to the 4th, I'm taking something to a power, raising that to a power, so I multiply those exponents, I get y to the 20th. So that's an example of kind of, and you'll see some of these in the homeworks, and really they get pretty complicated. Then the last rule is the quotient rule for exponents. My example here is if I have something like, say, 2 to the 5th divided by 2 squared, what happens, what that repeated multiplication looks like, 2 to the 5th is 2 times 2 times 2 times 2 times 2. So I have this. 1, 2, 3, 4, 5. And then my denominator, I have 2 squared, so that's 2 times 2. And now the way that cancellation works in fractions is if I have a factor upstairs and a factor downstairs, I can cancel those out. And so what happens is every factor of 2 downstairs cancels one out upstairs, and what's left is just 2 times 2 times 2, so that's 2 to the 3rd. And what that rule in general looks like, I don't know why I didn't type this, quotient rule for exponents. If I have something, so a to the m upstairs, and I have a to the n downstairs, what that ends up giving me is that base, so a to the power of m minus n. All right, and that's the last rule. So make sure you go through these homework problems. As always, please let me know if you have questions. The My Math Lab is posted as well. And 5.2 video will be coming soon.